We've seen so far that the product of mass times velocity, remember velocity is a vector, is momentum. And that will stay the same if there are no external forces acting on an object. That's what Newton's first law tells us. But if we want to change that momentum, then we need to apply a force, and the longer that we apply that force, the greater the momentum changes. So we have that relationship of the change in momentum is equal to force times time. Force times time, we have a new term. We call that impulse. I want to show you a graphic way that we can end up showing how those quantities can be added and how momentum can change when a force is applied. Now in this case I have a bowling ball. Its mass is 5 kilograms and it has an initial velocity of 0. And to that I'm going to apply a force of, let's say, I don't know, let's say 10 newtons. I'm going to apply it for 3 seconds. Let's see how much the momentum changes. From our relationship here, remember our change of momentum is also called the impulse. So our impulse, and that actually has the letter J. Okay. The J is equal to 10 newtons, and that's going to be to the right, times 3 seconds. We see that we have 30 Newton seconds. And now let's take a look at that. Okay, we know we have 30, and remember a Newton is a kilogram meter per second squared, and that times a second. Let's go ahead and cancel some of this out. Hey, we see that the units work out to 30 kilogram meters per second. That's exactly the unit we've been using for momentum. So impulse has the same units as momentum, or a change of momentum. Let's do that using our graphic technique now too. So go ahead and I'll, let's see, put this on my momentum chart. So I see I have 5 kilograms. 1, 2, 3, 4, 5 kilograms, but 0 velocity. So it's really just laying right along here. My rectangle really has no area, right? Because if I have base times height, my base is 5 kilograms, my height is 0. My momentum here is 0. Let's see what we can do about adding impulse to that. That's going to be something new we'll add here. Now this new impulse graph, or impulse chart, we'll have, see, I'm going to add this. I'm going to have force, because remember force has direction. It can have a positive or negative direction to it. And then time. Time is a scalar. You know, there's no direction associated with that. So we have force in newtons, or time in seconds. We'll call to the right positive, and down or to the left negative. Let's see, we'll plot that for our impulse here. Okay, so force 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 newtons. Okay, and the time 1, 2, and 3 seconds. Let's go ahead and we'll end up creating a graphic representation of that. So I got a rectangle that's 10 newtons high, 3 seconds wide. Let me go ahead and highlight that. Okay. The area of this again is base times height. My base is 3 seconds times my height, 10 newtons, and I have 30 Newton seconds, which we saw before was the same as 30 kilogram meters per second. Let's go determine our final momentum here. Hey, so I know my mass stays the same. 1, 2, 3, 4, 5 kilograms. My total area is my initial momentum plus my impulse. I know that my final area is going to be 30 kilogram meters per second. This is over at 5 kilograms. So what's that final velocity? Well, now the width of my rectangle is 5 kilograms. I know the total area here is 30 kilogram meters per second. So the velocity must be 6 meters per second. So applying a force of 10 newtons for 3 seconds, we'll end up making this bowling ball roll at 6 meters per second. It will assume to the right after those 3 seconds. Okay, so let's take a look at this circumstance. Okay, now we have that same bowling ball, 5 kilograms, but now it's starting off with an initial velocity to the right at 3 meters per second. We'll calculate the initial momentum here. It's going to receive an impulse, a force of 8 newtons to the left for 4 seconds. What we want to do is find out what its final momentum is, and from that we can figure out the final velocity. Let's go ahead and do this a bit graphically. Okay, we see that 5 kilograms, 1, 2, 3, 4, 5 kilograms at 3 meters per second. That the area of this will be 3 times 5, 15 kilogram meters per second. Let's see the impulse. The force is to the left, so we know that that's going to be 8 newtons to the left, or negative. 1, 2, 3, 4, 5, 6, 7, 8. And it's going to last for 4 seconds. 1, 2, 3, 4. Let's go ahead and sketch out the area there. Okay. Notice that this is below the x-axis, so this is going to be a negative value because we've been calling to the left negative. I have negative 8, my force is negative 8 newtons times 4 seconds. I get 8 times 4, that's 32, so negative 32. Remember, a newton second is the same as a kilogram meter per second, so that's going to be a kilogram meter per second. Okay, hey, we just end up looking at the differences between these areas. One's on the positive side, one's on the negative. What do we have? So let's go ahead and add this up. We have 15 kilogram meters per second, and we're going to add to that a negative 32 kilogram meters per second of impulse. That's to the left. Okay, I look at that, and I have a negative 17 kilogram meters per second is going to be the area of our rectangle. We know that the rectangle still has to be 5 kilograms wide. There's no change in the mass. 1, 2, 3, 4, 5. Okay, and let's see. And what do I have to do for velocity? I know my velocity is going to be equal to about 17 kilogram meters per second divided by my 5 kilograms. And it tell me it's about minus, what's that, 3.4 meters per second. So 1, 2, 3, 3.4, somewhere around there. Okay. The area of that, sorry, minus 17 kilogram meters per second for this area. And the velocity, negative 3.4 meters per second, or its velocity is to the left. So really the big takeaway in this is we end up plotting momentum in a velocity versus mass graph, or we plot impulse in force versus time. The area that we get for each of these remains the same. Okay, good luck with these.